Hello again, everyone, and thank you for attending today's webinar, Tips for Additive Manufacturing in Metal, brought to you by Design World Magazine. We would like to thank our presenter, Tom Pasterik from ExOne, for being here today. I'm Leslie Langnaw, a Managing Editor at Design World Magazine, and I will be your moderator. Just a few housekeeping details before we get started. This webinar will be available afterwards on our website, designworldonline.com, and you will also receive an email link to the webinar sometime today or later on today or tomorrow. The question and answers, we will have a question and answer session at the end of the presentation. Tom will be available. And if you would like to tweet about this webinar at any time during it, please use the hashtag DWWebinar. You can go ahead and submit your questions at any time during this presentation. You'll see that on the box. Right now, I'd like to introduce you to Tom Pasterik. Tom is Manager of Application Engineering at ExOne. As part of his duties, he reviews parts for printability, as well as ensures and makes improvements throughout ExOne's processes. He has worked for the production department, but also aided the engineering, marketing, and R&D departments. He has a degree in industrial design and a degree from the Art Institute of Pittsburgh. And without further ado, I'm going to hand the microphone over to Tom.
Hi, I thank all of you for taking some time out of your day to join the webinar. Hopefully you guys will find it exciting, and hopefully there'll be several questions at the end. So I've been working with ExOne for about 3 years now, and a little bit of our company overview is that we're a leading additive manufacturing company that is dedicated to industrial manufacturing, to the industrial manufacturing sector. ExOne is also a global supplier of industrial 3D printing systems. We offer the systems as well as offer designs and manufacturing of 3D printed parts. So whether you wanted to buy a machine from us or just prototype or run low volume, high volume production parts, our facilities can handle that throughout the globe. ExOne production services are located throughout the United States, Germany, and Japan. And I do have to apologize, my slide's not updated, but we have expanded to the South Americas, as well as other parts in Germany. As well, ExOne systems are available to print in a variety of industrial materials with the largest available build box. So this is just showing you kind of where we're at throughout the map. We have PSCs that are popping up in several new locations. We will be having a new facility on the west coast of the United States, as well as in South America, and another one in Germany. Kind of get you guys excited about the webinar, our products produced. I'll start from the top left, is a sand core mold. ExOne basically prints in direct metal, or what we also call indirect metal. These are two different processes that we hold here at ExOne. The one on the top left is a large sand core mold that we can now take your parts to a foundry and run traditional materials through them. The next one to the right is an end suction centrifugal pump. It was a quick part display, so we rapidly manufactured the parts and assembled them together. The next one over is prosthetics. It's a prosthetic hand for a gentleman that unfortunately lost his hand and now can use his hand interactively and change different pieces very rapidly with our process. With the direct metal process as well, the small sand core, or large metal mold, we produced rubber tires for a project that we had here at ExOne. The bottom left part is a heat exchanger. So wherever you can print cavities that you cannot traditionally manufacture out, such as with the drilling and mold package technologies, we can now do that. Just as long as you have one porthole that we can release the sand or release the metal, we will be able to produce that part. The next one is a fuel injector connector. This is the, if you can see my mouse, it's produced out of sand, and we'll cast traditional materials throughout that part. The next one is a half impeller that we used for display, and then the far bottom right one is a is a jet engine core. So hopefully that'll get you kind of excited on what we can do here at ExOne. A little bit about ExOne's overview. We are the leader in industrial 3D printing and additive manufacturing. Basically, what is additive manufacturing for the novice user of additive manufacturing? It is a process of making solid objects from a digital model by layering powdered material in a binder. We also, changing from manufacturing paradigm, I will describe this a little bit later with a different model due to the difference between 3D printing and what actually additive manufacturing would be, and how quickly that process can change. And then which product would be right for you, whether you want to buy a machine from us or you would rather produce parts through us. We offer both services. A lot of our customers that would buy a machine, basically what we call a test drive, and they'll test drive our process for about a year, just printing parts, and then they'll make that determination if they want to buy a machine or if they want us to continue parts. Either way is fine with us. Some distinctive technology features. I like this slide because it kind of shows you how long we've been doing this, and this is one of our newer pictures, and it was from 2009 on how large of a platform we can print. We have one of the largest build envelopes, and finely detailed complex shapes are right up our alley. Our print speed is pretty much unmatched right now with any other comparison with any other 3D printing company. And our final product accuracy, we can print plus or minus 5% of any given feature. So a circle with a round hole in it, we can produce inside diameters and outside diameters for a plus 1% of each of those features. The industrial grade material, that is one of our main focuses here at ExOne. We stay on top of whatever industrial graded material is popular right now. We will be going after that. We have a full facility right now that's just responsible for releasing new materials called ExMol. I'm stuck. Really bad.
There we go. Hang on a second, Tom. We're having a little bit of difficulty here. Let's see if we can get it set up. There we go.
Okay. Okay.
Let me know when you're ready, Leslie.
Anytime you're ready.
Okay. I apologize for the difficulties there. Before we move on to the direct metal process of what ExOne is, there are other additive manufacturing companies that are using industrial graded materials. These companies are such as EOS and Renshaw. We do not like to compare ourselves as competition, just more of a milestone or not a milestone, but a goal to at least produce parts as well, or if not better than them. But there are different advantages depending on what you are expecting from additive manufacturing. For example, EOS is their surface finish is a lot greater or a lot more refined than what ExOne can offer you. But ExOne, if you'd like to produce parts quickly and at a cheaper price, same quality, we are the experts in that situation. So to move on with what ExOne does, we are a binder jetting company. Whenever it comes to direct metal processes, we offer materials such as 3/16 stainless steel that's infiltrated with bronze, as well as 420. And now we just introduced iron that's infiltrated with bronze, as well as bonded tungsten. A lot of these materials we'll use for rapid manufacturing for quick prototype. Some of these prototypes turn into low volume or high volume production for us, as well as somebody that would buy the machine, they could use this for prototyping or low volume, high volume. Our bonded tungsten is more used for filters or drains or strainers in different applications. The additional material systems are currently in development, but they claim to issue every 6 months a new material. So it's pretty exciting right now with what ExOne is doing. The 3D printing process, really quickly, and I'll describe here later, is we'll print the part, cure the part, depowder, sinter, infiltrate, and then we'll anneal the part. After that's all said and done, you'll have your part on your desk in about 3 to 4 weeks is our turnaround time. Depending on part quantity, that may lead out to a little bit longer. But if you engineers that have the last quick idea and want to get it to the meeting, and you only have 3 to 4 weeks, then we're definitely your application. Our build volume in direct metal, so this is where we're jetting binder onto powdered metal, is 30 inches by 15 3/4 by 15 3/4, and our build speed for machine buyers is 6 millimeters an hour, or that's almost 1/4 of an inch per hour, so fairly quickly. Our indirect metal process is what we call our sand process, and this is where we 3D print the sand core molds. I don't know or not. Okay, so hopefully we're all on the sand process page, but this is where we 3D print large sand core molds or small sand core molds, and then we can take these sand core molds and send them to a foundry and run traditional materials through them. Whether we want to use silica sands, synthetic sands, or any other casting material, we usually will print those for you, and then we can send those to the foundry, and you can cast your traditional materials. Digital production of sand molds and cores eliminates the need for hard tooling, so that drastically cuts down on your lead time. Not only does your lead time cut down, but your storage space cuts down. So where you have a large facility that will house large metal patterns or wooden patterns, you can now store this all on a USB or on your server at your computer. The standard foundry materials are used, enabling easy integration of the molds and cores into existing manufacturing and foundry procedures. We see a lot of our customers will use this process for prototyping. A lot of our customers use this for low volume or high volume productions. This also offers design freedoms. You are now taking advantage of additive manufacturing, so where you can print a part inside of a part and then cast that part, you cannot do that traditionally. It's almost the lost wax process whenever it comes to our sand printing process. This is our largest build box, and our build volume is 70 inches by 39 inches by 27 inches deep. So fairly large. It is all completely automated. These are some of our systems. So the system all the way on the left, the small little one, is the MLab. Great for R&D work. Quick small box, around 2 inches by 1 inch by 1 inches deep. The next one to the right of it is the MFlex. The MFlex will be able to produce whatever powdered metal material you'd like to put into it. We will be able to bond those particles together. This is our newest machine. It has a build volume of 10 inches by 15 inches by 15 inches deep. The next one to the right is the M-Print or / the S-Print. We can convert this machine from a metal machine to a sand printing machine fairly quickly, and then we can offer that to our customer. The next one, the farthest one on the right, is what we call the S-Max, completely automated, very large build box, and this is our largest build box and one of the largest 3D printing build boxes across the globe right now. So ExOne's process, how we produce parts, whatever CAD program you're developing, such as SolidWorks or Rhinoceros, anything even from ZBrush, if you're going to do sculpting, we'll just upload the file just as long as it's a binary STL file. We'll send the print, and then basically that print will be printed until finished. Once that's finished, we'll put it into a curing cycle. The whole build box actually comes out of the machine and then into the cure cycle. The cure cycle, depending on part complexity or part quantity, depends on how long that will take. This is where both steps of the process, both direct metal and indirect metal processes, are the same. They do need time to cure, but once they cure, we will depowder the parts. Sometimes those parts are depowdered and then sent to the foundry to allow for process. But if it's a delicate sand core mold, then we'll produce and send the part to the foundry, and we'll depowder the part at the foundry so we don't break that complexity. So now that loose sand is acting as a support material. Once that's done in the foundry material, the foundry material will now be poured and then casted into the traditional material that you would prefer. Anything from aluminum to titaniums, tungstens, high-grade stainless steels. If you're printing in direct metal, we will then put it into a large vacuum furnace. These parts sit in a small graphite crucible or large graphite crucible, depending on the parts and the part complexity, and we'll supply bronze to that stainless steel part. Once that part is covered with covered with grit, we'll put it into a furnace, and around 1100 degrees, that bronze will liquefy, and that printed part will act like a sponge to water, basically sucking up and infiltrating the part. The part's around 95 to 97% dense. So this is where the sintering and infiltration part is happening here down on the bottom right. ExOne's process, on the left-hand side here, you can see that the sand process takes approximately 1 day from start to finish. That is just for printing. The glass is approximately 3 days from start to finish, and that is a final product. The metal is around 3 to 4 days, depending on part size. If you had a dedicated process to this, such as a furnace, a curing oven, and a printer. So we're going from 3D printing and just prototyping to optimizing for a complete manufacturing facility. If you use these printers, we can then transfer basically like any other facility we'll use is transfer belts and eliminate the use of human error or human interaction with those parts. One slide. Okay, so ExOne in the factory. Not too much. Okay, so hopefully everyone has seen the title slide ExOne in a factory environment. On the left-hand side here, we are just doing one-off parts. Basically just quickly rapid manufacturing or prototyping the part. This is just for one part and just basically getting your idea out there. You can see that we have the print station, curing station, depowdering, and infiltration. All handheld and handmade parts as well as handmade transfers. We can go from the production of rapid prototyping to mass production. Here at ExOne, we have 12 printers with only 2 people running that whole facility, where you need, instead of each printer or traditional manufactured part, such as a CNC machine, you'll need 1 operator per machine. With our process, we don't need that. We can fully automate from print to cure to depowder to final product fairly quickly with very small human interaction. The advantages of additive manufacturing, think completely outside of the box is what I like to tell a lot of our customers. It offers complete design freedoms to get away from traditional molds, cores, CNC toolpath layouts. You don't have to worry about draft angles. The part geometry is endless, and the functional working prototypes, now that you print an industrial grade material, can now just be placed into real life applications and tested. So you don't have to prototype with plastics. You can go right from an EOS machine or a Renshaw machine or an ExOne machine and go right into a real life application. A lot of those facilities, such as EOS and Renshaw and ExOne, will be able to produce low volume and high volume productions as well. Prototyping, like I said, can turn into low volume, high volumes. Advanced vending schemes and integrated rigging features are also possible. So for those guys that are casting parts, we can actually print in the gates, the gating systems, as well as the cores. That is kind of difficult right now with traditional manufacturing, where it is more labor intensive. We just change it on the computer file. That kind of leads into the last point, is that we can change those, whether you're printing direct metal or indirect metal, in the matter of seconds. Just a quick example how we took advantage of additive manufacturing. We took a control arm that was traditionally manufactured and was proven that it was completely optimized, and or strength could be taken away from that control arm. This control arm was off of a domestic supercar, and we pushed the boundaries of 3D metal printing. We also developed new workflows. So we didn't realize what we were doing until halfway through the project, and we came up with some new terms and new processes for what the benefits that 3D printing offers. The overview was to reduce the weight while still retaining the same structural properties. We didn't really go after the strength as much, but after the end of the project, we realized that we could produce a stronger control arm at a lighter weight. So the idea was to take that existing production part and provide further optimization and modeling in pre-constrained areas. These were the pre-constrained areas, and we wanted to produce those printed sand mold packages, and be able to have a physical working part and then do testing on that part. The next step was to do a conservative constrained direct metal printed part, and then our last step, which we didn't get to finally print at the end of this project, but we just recently printed here in our facility, was an unlimited direct metal printing. We also call this a VOI, or a blue sky. That design kind of looks like, it will look nothing like what you actually see here on the computer screen. We'll basically take these control points, this was one of them, and then the second control point and the third control point, and we applied forces to them digitally, and it basically chewed a block up digitally, and it made a control arm look like nothing you've seen before. So we took that idea and decided to spread cellular structure. We took the standard SolidWorks file and imported it into Rhinoceros. Rhinoceros is a NURBS-based design program. I know a lot of engineers do not use that, but if you can model as much as you can traditionally and then import to Rhino, we can definitely take control of that now. A plugin called Uforma. Uforma lets you use unlimited geometry. So what kind of cellular structure you could provide, or stochastic growth. Blending was very easily with this program. Trying to produce something like that in SolidWorks or Rhino, you will not be able to. The part is just too complex. That being said, we had to go through and design new, we wanted to see what our cellular structure really wanted to look like. So we went through several variations, and these variations were very quickly and easily be able to be manipulated. So as you can tell, we tried spheres and circles. We tried small I-beams, and basically this program and this plugin took advantages of additive manufacturing. We now can grow it's needed of creating a part that, oh, we need it to be structurally sound, and we should increase it and make it thicker and thicker and thicker, or wider, and how a traditional manufacturing job shop would request you to. We now just grow that in areas. We can eliminate and increase strength or maintain the same strength. So once we picked our structure, we picked the areas that we wanted to continue. So the initial reference was basically a cellular structure. This kind of shows you how quickly and easy. On the left-hand side here, this was a solid block, and we kind of just spread a cellular structure that we thought would pass the FEA analysis. and then we applied it to the certain areas that we wanted to eliminate weight and eliminate material. Very quickly, very easily. That cellular structure was then applied, and then we ran our control arm against a traditional control arm that was optimized and was on a production car from 2005 and 2006 to our now what is our base model control arm. This is our final model, and as you can see that we have not caused any problems with stress or strain of the material of the part, and it has passed after 2 or 3 different renditions. It has passed the FEA analysis software. So once it's passed the FEA analysis software, we then took it to the indirect metal facility at ExOne and printed the part. So on the top left here, the mold package design was developed in SolidWorks. That part was then sent to print to the right here, showing the printed mold package. Once that was done, being sent to the foundry, they casted the part out of the traditional 3/16 aluminum. And then, like lost wax, we busted the mold package loose, and the sand is crumbled and is then recycled. And then to the right here is the final product. About a 3-week turnaround time on this product. So the second step was to devise a plan to create an advanced control arm that is modeled with free constraints. So we took what was the base model here to the right, and we basically expanded it to the next part of the control arm that we'd like to. And if you can see up here on the right-hand side, there's small cellular structures that are holding this support or web material. So it's not a straight through, just holes punched through, but these cellular structures are grown to certain thicknesses very quickly and very easily. So once that was modeled, we then sent it to the FEA analysis software. Once that was done, there were several renditions that we had to go through, but as you can tell, we increased some strength to the bottom right here, and that wasn't even our intentions, but with the cellular structure, it controlled the pressures and the load of the control arm, and gave us a lot lighter weight control arm. Once that was done, we went to print the control arm. This is our direct metal printing process. Basically, we'll just be laying down a binder across a powdered metal bed, what we pull directly from CAD. Our direct metal printing process basically stacks up layers of material, so we'll spread powders. Depending on certain size powders, we'll spread it at different layers, and we'll get a binder. Once the binder is done, we'll spread powders across the print bed again, and then jet a binder again, basically stack that part up throughout the STL file. We'll put it in, and then after cure is powdering. Depowdering will suck up all loose stainless steel powder, and all that loose stainless steel powder acts as a support material, but is not thrown away. It is 100% recycled back up to the process, and that loose powder that was holding the part will now be a part later in its life. We'll then take the powdered part, put it into a crucible, and then we'll infiltrate it with a large vacuum furnace. Once that part's done, after a 12 to 14-hour cure time, or infiltration time, depending on part complexity as well as part quantity, you'll have your final product. Once a product is finished, we can bead blast that part. We can drill, tap, machine, powder cutting. You can do additional stainless steels. We can do now with a R420 stainless infiltrated with bronze. As you can see on the right-hand side, we have full complete accuracy of the printed part from the digital model. Very nice blending, as well as structural support inside the control arm. In the beginning, I was talking to you about how we didn't even realize that we invented or came up with a new process, but we came up with this process and we labeled it direct fabrication. So direct fabrication goes from the idea or quick sketch input to a model. Once that model is created, we'll check the performance with simulation, whether it's an in-house or outsourced software that'll check the parts. Once a part comes back from FEA and the parameters need changed from the base model, completely, very easily. In a matter of minutes, we can change that structure and then get an export a file to run FEA again. So this is very quick and very powerful. This is where another part of direct fabrication changes the way we can now manufacture parts. We can now change our parts from printing in an STL file. We can go right from the CAD file. So we do not need to export as an STL. Exporting as an STL eliminates, or if we print directly from CAD, it eliminates the problems that STL file formats create, such as overlapping triangles and voids, poor intersections. So we can directly print right from CAD right to the fabrication, and now we can take advantage of our printer resolutions. So now we can print at whatever printer resolutions we'd like to use. I'd like to see a lot of companies, anybody dealing with 3D printing and working in an STL file, go to this direct fabrication. Once that part's fabricated, we can then take it to a physical test, and if it does fail, all we have to do is go back to optimize and change the parameters and run it through the performance cycle again. Very quickly, very easily, and then we can send back the print. So instead of building mold packages or seeing something out, we can now rapid prototype your parts. This was just some of the project specifications from the control arm. As traditionally casted, you can see here on the bottom was the traditional arm was 5.78 pounds. The casted aluminum, where we did not get too, we were kind of cautious and just printed what we called our pervaded or our base model, was 5.4 pounds or 5.04 pounds. If we had the ability to print this part in aluminum, that part would be 4.57 pounds, so for a weight reduction of 1.21 pounds, which is very significant in a domestic supercar. So you can imagine where you could take this in any industry, whether it be downhole applications, gas and oil, pumps, props, turbos, or any other functional working part on an automobile, airplane. And to kind of prove our theory, we 3D printed the actual version of the traditional control arm, which was 14.4 pounds, and our 3D printed version was 13.2 pounds. We were talking earlier that we wanted to do a third control arm, and this is more of a conservative route because we needed to finish our project, to be honest, and we are still modeling what we're calling the blue sky design, but we designed small I-beams and spread them throughout the control arm. And as you can tell, we've only grown them in certain areas. So where we didn't need as much supportive material, we left the cellular structure large and thin. And then where we needed it stronger and to control the weight to go into the different control points, we grew it at a more dense rate. So now we're really taking advantages of additive manufacturing. So think of something how it would actually be grown in nature. We don't have to design for the process now, or we don't have to have the design be controlled by the process. We're actually designing for the process now. So we can now take advantages of that. Just some services that ExOne offers is direct part production, part design, material development, R&D services, quality control, and machine purchasing. That's the end of my presentation, and I will let Leslie take control from there.
Thanks, Tom. That was a very interesting presentation, and we have several questions that have come in. So I'm just going to go ahead and start here. One of the first questions that came in was regarding your printing of sand molds, or is it an SLS process that you sand cast and then burn out to pour in the metal? So I guess there's, could you maybe go into a little bit about the two different types that you offer?
Yes. Is Leslie okay?
You want me to say that again?
No, I don't have to click on it. I'm good.
Yeah, you're good.
Our indirect metal sand process is we 3D print with a binder jetting system, and we'll basically print that part with all the features inside of it, and that sand that's loose that has not been touched by the binder acts as a support material. That support material will be vacuumed out and blown out with air tools before it goes to the foundry, or once it gets to the foundry if the part's delicate, and then we will cast those parts. will be no powder inside the cores or molds. Nothing will be burned out. The sand gets vacuumed out.
Okay. Another question that came in is, do you use UV post-curing for any of these processes, or is that needed?
No, we do not use UV post-processing.
Okay. Can you print copper parts?
We do offer printing bronze infiltrated with copper, and we are in the process of, it's on the radar for printing copper parts.
A question has come in about timing. You mentioned a turnaround time of 3 to 4 weeks, but the questioner says that it seems to take about a day to produce a sand part. Can they get a sand part in 1 to 2 days?
If you had, I apologize if I confused you, with our facilities, and if you use our job shop services, that is our turnaround time just for the high workflow that we have here. We have a large amount of customers that will print through us, and that is our quickest turnaround time. But in my support, I will tell you that if you had a part and a process dedicated just to this, so if you would buy a machine, then you could have parts printed and then printed in within a day.
Okay, this is an interesting question, and I'm going to, all right. This person is saying that additive manufacturing is not known for producing functional working prototypes, but you mentioned that it is an advantage of additive manufacturing. They want to know, are you referencing ExOne parts in particular, or is ExOne parts able to be functionally tested for things like electrical, thermal, and optical properties, chemical resistance, and so on, similar to what subtractive manufacturing techniques handle? It's my understanding that additive manufacturing can produce functional working prototypes.
Correct. Depending on the application that you, depending on the material that you do print in, such as a 3D systems or an object, if you have a plastic application, I don't see any reason not produce parts and use them into a real-life application. Whenever it comes to ExOne's process, I can speak truthfully about that. We can 3D print a prototype part, and you can take that 3D printed part and put it into real applications depending on the application. A lot of our customers are prototyping with us, and they like our parts so much that it turns into low volume, high volume production.
So it's my understanding that either with 3D printing or with additive manufacturing, if you're working in parts, those in particular can be used as final end-use functional parts.
Absolutely, yeah. Whether it's with EOS or Renshaw, all those parts, as well as ExOne, can be drilled, tap machined to spec, or if not already in spec from the 3D printing process, and then they can be put into real-life applications.
Okay, here's another question. Now, how do mechanical properties of a 3D printed part differ from those of a machined part from, say, a solid material like aluminum or steel? Is there a difference?
Whenever it comes to EOS machine or Renshaw machine, I cannot speak of their materials. I do not know their material properties. But with ExOne's stainless steels, they are 420s and are 3/16 stainless steels that have been infiltrated, meet or exceed the traditional standards of a 420 traditional stainless steel bar stock. So that's in tear, shear, tensile, and compression.
Okay, I think seem to be missing a question. Whoops. Okay. Can you print in titanium or any of its alloys?
We will be offering titanium. It's on the radar, but I cannot tell you when we will be able to offer that material.
Okay.
But that is one of our focuses.
Do you use or need any special sand material?
No, we use silica sands in any traditional sand casted part. We'll use that material. The thing that we have proprietary on is our binders.
Okay. Have you done any tensile strength tests on the printed parts versus the casted fabricated parts?
Between both processes, I do not have that information. I know we've done a few things, but I can get you that information if needed.
Okay. And have you had any experience with medical implantable devices?
We've had a few customers, but due to our materials, we don't allow for embodied material or embodied applications, such as the medical fields, just due to our stainlesses.
Okay. And let's see, can you print threads or screw attachments?
We can print threads and screw attachments, but we do not guarantee them. We can print them to near net shape, but then you'll have to go in and drill and tap or machine those out. We usually recommend to the customer to allow a little bit of extra material and then have a post process.
And what are the disadvantages of your processes?
The one thing with our process is we are only printing 0.5% of any given feature. We are not to CNC printed tolerances. So we can get to near net shape, and we're getting better and better due to our printers, as well as particle sizes and the new technologies that are out there. And the others are our surface finish. Our surface finish will need to be polished if you are looking for an application for a smooth, polished surface.
Okay, this question is, during the infiltration process, you mentioned that the material used to fill the gap is bronze. If the material powder used is stainless steel, would the infiltration material still be bronze?
Yes, we'll use stainless steel, and we will infiltrate it with bronze. Due to the relationships between those two materials, they are perfect for one another for our process. I can tell you that we do offer stainless steels, 420 and 3/16 that are infiltrated with copper as well.
Okay. Do you have any capability for direct metal laser sintering? And would that produce parts that require the bronze infiltration? I think DMLS is a trademark term.
Correct. Yes. No, we do not. We are a basic binder jetting printing company. We do not offer laser sintering, and we are not going in that direction.
Could you maybe give a couple of minute discussion on the difference between the binder jetting and the direct metal laser sintering?
No, yeah, I do not know laser sintering as well. I apologize.
No, that's okay.
I just don't want to give the wrong idea.
Okay. How do the printed parts handle vibration and shock?
With our compression and tension, we are close to a traditional 420 stainless steel part. That being said, in those categories, we are a little bit below the standard of what tensile strengths are, but we're in the process of what we're calling annealing parts, and that will give us that strength. So whether you want a part that is more of a spring material, or we can bend that material, then we will not anneal the part, and that part will be able to do that. But we are in the process of doing more case studies, so a lot of our material properties are on our website as well. We have several spreadsheets out there. So.
Okay. Now, can the stainless parts be welded, or does the bronze cause issues with welding?
No, the stainless steel parts that are infiltrated with bronze can be welded, whether it's TIG or silver soldered. They can be welded. Anything that you can do traditionally with a 420 stainless steel or 3/16, we can do with our hybrid materials.
Okay. Are there any issues with a difference in coefficient of thermal expansion of the two materials?
I do not know the answer to that one.
Okay.
I can have our guys in the R&D labs at ExMall develop that and show that to you.
Yeah, just a quick note to our audience. You see on the slide Tom's email address. Feel free to send some of these questions to them if they haven't gotten answered, or if you would like an expansion on the answer. Let's see. How do your layers interact? How thick is your minimum layer, and how much of the previous layer is fused to merge to the next?
With our binder jetting systems with direct metal, we are printing at a 30 micron stainless steel powders, and we're spreading them at 30 or 4 thou layers. Once that 4 thou layer is spread across the print bed, we'll jet a binder, and that binder saturates in through the metal particles just on that layer. And then once the next 4 thou layer of 30 micron stainless steel powder comes across it, that fuses throughout that saturation. So there is no layer gap, if that was the if that's the question.
Yeah, I'm not sure what that was, but that's okay. That was a good answer. Can these parts take high velocity impacts?
I do not have specs for that as well. ExOne is creating case studies for all these all these questions. So
these are very interesting questions.
Yeah, they are
very detailed.
That's okay. That's fine.
Okay. Could you go over again the tolerances of your printers?
With sandcore molds, it is going to be a traditional casted part, whether it's direct metal or whether it's investment casted or just a wooden pattern. It's going to be the same standards that you would get. With indirect metal, we're at plus or minus 5% of any given feature, and we are near net shape. We're not close to CNC. We're close to CNC, but we're not CNC yet.
Okay. Alrighty, I believe that's going to be about all the time that we have for today. Just a reminder that this webinar is being recorded and it will be made available on the Design World online website in a little while. And you will also receive an email link to it. In the meantime, if you have any additional questions or more specific questions for Tom or for someone else at ExOne, you see the phone number right on your screen, as well as Tom's email address. And I'd like to thank everyone again for attending this webinar. We hope you enjoyed it.